Thank you for inviting me to the Fields Institute. My title was already mentioned, so was my name. There is a URL, http://drorbn.net/fi20, and you can find the slides there, and later there will be the video as well. And I should say that my talk is off topic. So Hans and Will invited me, and probably because I was very near, right across the street, I told them I don't really have anything to say about not concordance and not homology. So they said, say something else. So I will say something else. It's completely off topic. It's also off topic for me. It's something that's been on my mind for a long time, and I never had the chance to talk about it. And I hope you'll find it as, well, modest for sure, and like a light conversation. The abstract is here. Hopefully you've read it. And if you can, please turn your video on. I would love to see you. If you hate me, I want to see it. Okay. Another thing is, since many of you have never been to the Fields Institute, here's a picture of the lecture room. So I'm speaking in front of this camera, of this screen. I'm watching you on this screen. The video camera is out here. My computer is here. And I'm challenging you to figure out what's visible outside my window. And let's start. So, there is a recurring question in knot theory, and this is, you get a knot invariant and you ask yourself, do we have a three-dimensional understanding of this invariant? And, C. Witten and the Jones polynomial. So the Jones polynomial came in the early 80s, and it was defined as a completely two-dimensional, in fact, originally one-dimensional, so from braids, and then later Kaufman found a way to see it two-dimensionally from a planar projection of the knot. But there was never, but initially there was no understanding how it is somehow a three-dimensional invariant. In what sense? Why is it an invariant of knots and not just of knot diagrams in some a priori sense? And Witten came and gave the Chern-Simons theory description of the Jones polynomial. And, it's a lovely description, but in some sense, it's useless, because it defines the Jones polynomial as a certain ill-defined integral on an infinite dimensional space, and go compute this integral. Doesn't really help you to compute or even to study the Jones polynomial in many places. Similarly for Chovanov homology, so the definition is completely two-dimensional. We still, to the best of my understanding, don't understand it in a genuinely three-dimensional way. So I want to talk a little bit about my perspective on this matter, but from a slightly different perspective. So we often think of knots as planar diagrams. So which means that three-dimensionally they are embedded in pancakes. Geometrically, they are, embedded in things that are very, very, very thin and very, very wide and long, i.e. pancakes. So here's a picture of a knot embedded in a pancake. The knot was drawn by Lisa Picerillo in a recent paper. The pancake was made and later eaten by myself, but I've embedded Lisa's knot in my pancake. Does it matter? So it matters in at least two places. So sometimes we make statements about random knots or about most knots. So we say things, most knots are hyperbolic. Okay? Most knots have a non-trivial Jones polynomial. And when we say most, the question is most relative to what? Is it relative to a random knot in a pancake or a random knot in a three-dimensional space? Similarly, when we talk about computational complexity, we say the complexity of computing such and such invariant is 2 to the power square root of n, maybe, okay? Now, what's square root of n? Is it the number of crossings, or is it the size of the knot if it was a three-dimensional object? Okay, so there is a difference between the two. But first of all, so here's what I want to talk about today, about yarn ball knots. So knots that are not projected to a two-dimensional plane. They look like this. Here's a yarn ball, courtesy of Heather Young. And here's another example. So this was a street art display on the Toronto harbor front a couple of years ago. So these were, it's actually a tangle, I suppose. These are tubes, and people could speak on one end of the tube and listen on the other end of the tube. And in between, there was this horrible three-dimensional knotted construction of tubes, okay? So does it matter? Does it matter that your knot is genuinely three-dimensional? So here's an example. So here is a yarn ball knot, and here are some measurements that are associated with it. So let the diameter be called L, okay? And then the volume of this knot will be L cubed, and I'm assuming that I made the knot out of a fixed width yarn. So maybe the yarn had width 1, and so the volume also measures the length of the yarn, how much yarn you've used in order to make this knot. And now let's compare it. Of course, I can project this knot to the plane, but let's compare the size of the projection to the plane with the size of the thing three-dimensionally. So if I project it to the plane, let's subdivide the ball into, so right, it will be projected to a disk, and let me subdivide the disk into 1 by 1 squares. Now, each 1 by 1 square has, well, most 1 by 1 squares will have L layers of strand behind them. And when you have L strands passing through a 1 by 1 square, you can expect them to cross L squared times. So the crossing number of a yarn ball knot of volume V is, well, L squared crossings per 1 by 1 unit, and there are approximately L squared units. So the total crossing number should be L to the 4th, which is V to the 4/3, the volume raised to the power 4/3, which means that you've lost, or you needed much more space in order to describe the knot than you needed originally. Originally, you needed, suppose you wanted to describe a yarn of length V, or which is embedded in volume V, well, you need roughly V memory cells. If you wanted to describe the planar projection, you need V to the 4/3. Okay, and maybe before moving on, maybe I should say that when I say things are approximately equal, I mean equal up to constant terms like pi's and powers of 2 and things like that. And in fact, later also up to log terms. So I will consider things proportional to the log of V or to the log of N to be equal to 1 when I write approximately equal. Okay, so here is a definition, except it's so informal that I shouldn't call it a definition, but a conversation starter. So, you know, if you want to turn on the microphone and turn it into a conversation, we can do it, okay? So I will say that a not invariant zeta, is computationally three-dimensional, or C3D, if the complexity of computing it, given a 3D presentation of volume V, is much less than the complexity of computing it given a planar presentation of size, crossing number, whichever else, however else you measure size, but of size V to the power 4/3. Okay? And you could expect that most not invariants will be C3D, because it sounds completely unreasonable that in order to compute a not invariant, you would first have to project it to the plane, thus squashing it and increasing the size dramatically. Okay, it just sounds so unreasonable. I mean, there must be a way, given a not, for most not invariants, there should be a way to compute them more efficiently without squashing them to the plane first. So I should say that this is far from a rigorous definition. It's really just a conversation starter. So it's time dependent. When I say the complexity of computing an invariant in 3D, it depends on what year you're doing it, how well you have learned how to compute, how clever you are. It depends on how naive you are in making your complexity estimates. So it's very, very rough definition, okay? But it has something, okay? So let's see a few examples. So example, let LK denote the linking number of a two-component link. And I want to claim that LK, the linking number, is computationally three-dimensional, okay? So precisely, the complexity of computing the linking number from a 2D presentation of size n is equal to n. Basically, you have no choice. You have to go crossing by crossing and check if it is positive and negative, count how many are positive, how many are negative, but you have to go, I mean, it's a relatively easy computation, but you still have to go crossing by crossing. Yet I claim that if a knot is given three-dimensionally, like a yarn ball within a volume V, you can compute the computation, you can compute the linking number in time proportional to V. And since V is much less than V to the fourth, than N, which would be V to the 4/3, somehow the linking number is genuinely a three-dimensional invariant. Okay? So proof. So without loss of generality, we are looking at a link embedded in a grid. Here's a picture of a grid of the kind that I'm interested in. So basically, if the link was given just as a parameterized curve or a pair of parameterized curves, you would pick a grid which is finer than the sort of smallest feature. So basically, whose unit distance is less than the width of the strand, and approximate your knot by a grid knot on that grid. Okay, so I'm assuming that the link is made of straight line, is really a subset of this graph shown here. And in order to compute the linking number, I'm going to view this, I'm going to project this graph to the plane, looking at it from above, but slightly tilted. So it looks like this picture. Okay? So this is the same grid, but looked at from above. Now, so here's what a knot in a grid would look like And really, I should be telling you about links in a grid because now I'm talking about the linking number, but the pictures are the same. So here is a link in the grid, a knot in the previous grid, previously shown grid, projected to 2 dimensions. And if you look at it carefully, you can see that I've marked the edges by their serial number along the knot. So let's say I choose the base point and it's here, then the edges are marked 1, 2, 3, 4, 5, 6, 7, and so on, up to, in this case, I believe 64. Okay, now here is another picture in which I've retained the colors. So some of the edges are red, some green, and some blue. And I also retained the edges of the grid, which are not a part of the picture, which are not a part of the link, except I made them thinner. So you can still see the knot and you can also see the grid. So what's a knot? It's really a subset of the grid. So some subset of the edges of the grid, and each edge on this subset also carries a number where the number is the serial number in which you would see these edges if you walk along your knot. A similar description for links, I didn't bother to show it. Here's a bigger knot put in the grid. It's a bit hard to digest, but let me emphasize that asymptotically, the amount of information in this picture is V. You need V memory cells to store this picture. If you projected it to the plane, you would need more memory cells. You would need V to the 4/3 memory cells in order to store it. Anyway, so our projection, our grid projection is such that the blue lines, so the vertical edges, never participate in any crossings, and you can look at them and see it. However, the red and the green tend to cross each other a lot. And really, let me subdivide the picture into crossing fields, into little parts, triangles, which I will call crossing fields. So crossing field number 1, F1, is the top triangle here, and in it, about L green strands cross about L over about L red strands. There is similarly a crossing field F2, a crossing field F3, and overall there are approximately L squared crossing fields, or if I want to be precise, it's 2L squared, but again, to me it's the same. Okay, so there are approximately L squared crossing fields, and what I'm going to do is I'm going to compute the linking number by counting how many crossings are in each crossing field. Now, in principle, I should be counting with signs, right? But I may as well subdivide the problem into 2 or maybe 4 problems where I'll I'll basically look at the subset of the knot in which the strands are oriented, in which all the green strands are oriented up and to the right, and all the red strands are oriented up and to the left. And then I'll look at at another subset in which all the green strands are oriented down and all the red strands are oriented up, and so on. So this way I can subdivide the counting problem into 4 simpler counting problems in which I don't have to worry about the signs. Okay? So without loss of generality for the purpose of counting, all strands are oriented the same way, so I don't need to worry about signs. Okay, again, worrying about signs will double the computational complexity, but I don't care about scalars, about multiplying by 2. Okay, so so L squared times, we have to solve the following problem. So given a set R of red strands in a single crossing field, and given a set G of strands, of green strands in the same single crossing field. So really this means that R and G are subsets of the set of integers from 0 to L. Basically, all I need to know is the height within the z coordinate of the green strands that actually appear in a given crossing field, and the z coordinates of the red strands that actually appear in a given crossing field. Sorry, I went the wrong way. So given 2 subsets, I need to count how many pairs R comma G are there in which R is less than G, in which the red strand is below the green strand. That would be the count. That would be a count that will contribute to the linking number. So I claim that this can be done. So this combinatorial problem, given 2 subsets of the integers from 0 to L, count how many pairs are there which are below the diagonal. I claim that this can be done in time proportional to L. And so the overall computation time is the number of times you have to solve this problem, which is L squared times L, which is L cubed. Okay, so of course this counting can also be done in time L squared. You just look, you just sequentially go through all RG pairs, and for each one you decide whether it's above the diagonal or not, and then you count the ones that are below the diagonal. Okay, but I claim that you can do better. Okay, so proof. So I'm going to describe a very simple algorithm. So you start with 2 counters. One counter is called RB, and it stands for reds before. And another counter is called CF, and it stands for cases found. And you slide a pointer from left to right along the interval from 0 to L. So when the pointer is at the very left, so when the pointer is here, the number of reds to the left of you, so reds before you, is 0, and the number of cases found, namely the number of pairs R less than G, which are to the left of the pointer, is also 0. And then I start moving the pointer. Every time I cross, so every time I go across a red dot, so a member of the set uppercase R, so every time I go across a red dot, the number of reds to the left of me goes up by 1. And every time I cross a green dot, the number of pairs RG such that R is less than G is increased, and such that both R and G are to the left of my pointer. So this number is increased by the new RG pairs that are thus found, and the new RG pairs that are thus found are all the ones in which the G is the green we just passed, and the red is any of the reds to the left. But I know how many reds are to the left, that's RB. So every time I cross a green dot, I'll increment the number of cases found by the number of reds before. And then at the end, when my pointer will be on the very right, the number of the counter CF will give me the linking number, or will give me the contribution to the linking number from this crossing field. Okay? How long did this computation take? Well, every motion took 1 unit of computation, either incrementing RB or adding CF adding RB to CF. And I needed to move the pointer from 0 to L, which is length L, so the computation took time L, and I've just proven to you that the linking number can be computed three-dimensionally more efficiently than, or can be computed on a three-dimensional presentation of a knot more efficiently than on a two-dimensional presentation. Questions, comments? Okay. So here's a great embarrassment. You know, I would expect most knot invariants to be C3D, to be more efficient computationally given a three-dimensional presentation of the knot. But I don't know any knot polynomial, none of the knot polynomials that I know, the Alexander Jones, Humphrey PT, Kaufman, none of these, and no Reshetichin to Rayev invariant that I know can actually be, maybe except for the ones that reduce to the linking number, can be computed three-dimensionally more efficiently than two-dimensionally. Likewise, I don't know if any knot homology is somehow genuinely three-dimensional in this funny sense of mine. So, you know, maybe it's an embarrassment, maybe it's a cause for optimism. Maybe it's telling us there is still something very basic we don't understand about the Jones polynomial. So can we understand the Jones polynomial three-dimensionally, not just well enough to say big words about quantum field theory, but also well enough to compute it better? I don't know. Okay, I should say that similarly, I didn't have to use computation time. So suppose eta was a stingy quantity associated to knots, so a quantity that we expect to be small for small knots. So maybe the hyperbolic volume, maybe the genus, maybe the knotting number, okay? So I will say that eta has savings in 3D or has S3D if its maximal value on all three-dimensional knots with volume V is a lot less than its maximal value on all two-dimensional knots of size V to the 4/3. So probably it is true, we didn't write anything, we didn't even formally finish it, and I don't really understand hyperbolic knots well enough to speak about it, but probably the hyperbolic volume has this property. But then another great embarrassment is that the genus of the knot, which is so obviously a three-dimensional quantity, I actually don't know if, you know, if you're given a yarn ball knot, if there is a ciphered surface that that you can derive without first projecting or doing something equivalent to projecting your yarn ball. So I don't know if you get any savings in 3 dimensions for the genus of the knot. Anyway, but now I want to go back to computational complexity. And I want to say that if zeta is a finite type invariant of type D, then it can be computed, given a 3-dimensional presentation, in time proportional to V to the D. Now, it is already known that you can compute finite type invariant of type D and from a two-dimensional presentation of complexity n in time roughly n to the power d. So you can expect that that would be the best. So namely, you can expect that for at least most finite type invariant, that the computational complexity will be approximately n to the power d. And since n to the power d is a lot more than v to the power d, then this theorem says that most finite type invariants are really three-dimensional. Okay, or you actually gain something by embedding, by not projecting your knot into two dimensions. There are actually a few exceptions. So in fact, a generic finite type invariant of type D can be computed in time n to the d, but there are some exceptions. So if you look at the coefficients of the Alexander polynomial, then since the Alexander polynomial can be computed in bulk in polynomial time, the whole Alexander polynomial can be computed in polynomial time, even the high degree coefficients, which are finite type invariants of a relatively high d, can be computed efficiently. And there are a few other examples of polytime computable knot polynomials, and then the coefficients of these can actually be computed more efficiently. And so the theorem, and so the conclusion from the theorem does not hold for these. Anyway, the next thing I want to tell you is I want to explain why this theorem is true. So, but first a reminder. So what's a finite type invariant? So a type D invariant is an invariant that vanishes whenever you evaluate it on, so let's take D equal to 3. So a type 3 invariant is an invariant that vanishes whenever you evaluate it on 4 cubes, 4-dimensional cubes of knots. So sets of 16 knots that are generated in the following way. You take a knot, you mark 4 of its crossings, and at each crossing, you look at the difference between having the crossing the way it was in the knot, the way it was presented, or having it flipped. So you look at the difference between overcrossing and undercrossing here, and the difference between overcrossing and undercrossing here, and overall, you will get 16 knots when you look at all possibilities of choosing, you know, an over or an under in each of the 4 locations. You'll get 16 knots with signs, and I will say that an invariant zeta is of type 3 if zeta evaluated on the sum with signs of these 16 knots is equal to 0. Okay? So this is an analog of, it's a very natural definition, right? So differences are a bit like derivatives. There are combinatorial analogs of derivatives. Taking iterated differences is like taking iterated derivations, and saying that an invariant vanishes every time you differentiate it 4 times is the analog of saying that it's a polynomial of degree 3. So type 3 invariants are like degree 3 polynomials on the space of knots. Okay, so they're not polynomial valued invariants, they're numerical valued invariants, but they are polynomials on the space of knots. It's a very natural definition. Anyway, so not only it's natural, most coefficients of most, so all coefficients of all knot polynomials, when appropriately parameterized before categorification arrives, are made of finite type invariants. So there is a lot of finite type invariants out there. Anyway, so I want to tell you about how to compute finite type invariants, so I can tell you about how to compute them more efficiently. Okay, so first of all, given any, so every knot has something called its Gauss diagram. So say this is our knot. The Gauss diagram is obtained as follows. You walk along the knot, and every time you go through a crossing, you leave behind you a number, and you increment these numbers as you go. So you go and you leave 1 here, then 2 behind the second crossing, then 3, then 4, then 5, then 6, then 7, then 8. And these numbers are paired. So 1 comes together with 4. 1 is the upper crossing, the upper strand, and 4 is the lower strand of the same crossing. 5 and 8 are paired, 2 and 7 are paired, 3 and 6 are paired. And then you draw a long line, which really represents the parameter space of the knot. And you connect by an arrow any pair of numbers that was paired here. So 1 and 4 are paired, so I have an arrow going from 1 to 4. And in fact, I make my arrows go from the overstrand to the understrand, and I mark each arrow with a plus or a minus depending on the sign of the crossing. Okay, so that's the Gauss diagram associated with a knot. Now, a sub-Gauss diagram is simply a sub-diagram of degree 2 of this diagram would be a subset of the arrows, which has exactly 2 arrows in it. So for example, here is an example of a sub-diagram of degree 2 of the diagram given here. So 2 arrows I kept, these are the ones in the red, and I grayed out 2 of the other arrows. That corresponds to looking at subsets of the original knot in which you preserve only 2 of the crossings, or in general, another number of the crossings. Okay, so there is a map, phi d, which goes from knot diagrams into formal linear combinations of Gauss diagrams, and the map just maps every knot to the sum of all sub-diagrams of its Gauss diagrams, which have at most d arrows. So basically, so for example, phi 2 on this knot will be obtained by using 2 fingers and putting your 2 fingers at all possible subsets of order 2, of size 2, or less than, or 2 or less of the crossings. And for each subset, you write the corresponding Gauss diagram. Okay? So there is an underexplained theorem by Gusarov, Polyak, and Viro. And what I mean by this underexplained is, well, the theorem is in their paper. If you Google their names, you'll probably find the paper, but it's only there. And it's hard to read. And I was never able to fully penetrate it, though I have other reasons to believe it's true, but somehow I don't feel comfortable with the proof as given, and it's really time that somebody will give a fresh proof, conceptual, clarified, because it's a great theorem. Anyway, the theorem says as follows: every finite type invariant zeta of type D factors through phi sub d. So in other words, for every zeta, there is a linear functional omega on the set of Gauss diagrams of degree less than or equal to d, such that zeta is equal to omega composed with phi d. And in fact, it's if and only if. So if you find omega for which omega composed with phi d is a knot invariant, then this knot invariant is going to be finite type. This direction is actually easy. Suppose an invariant factors through phi d, I claim it's clearly finite type, because phi d, when computed on a cube of knots like this, is clearly going to be 0, because phi d is a sum of computations that involve touching the knot in d places. And if you alternate in d plus 1 places, then one of the places where you alternate is not going to be touched. And so phi d is not going to be sensitive to flipping and overcrossing to an undercrossing in that extra location. And so you're going to get 0. But the other direction is hard. So the statement that for every zeta there is an omega is hard. And it's what I'm going to use right now. So, well, I have my yarn ball knot or grid knot. It is embedded in a grid which looks like this, which really means that it's a certain path that goes through this grid, or said differently, it really means that many of the edges of this grid are blanked out, and all the rest carry numbers which indicate when you have passed through them. So 1, 2, 3, 4, and so on. Okay? And I need to count how many times a Gauss subdiagram of a specific type appears on such a knot. So I need to count, I need to highlight, say, 2 of the crossings of this knot, ask myself, do these 2 crossings form a specific diagram, say this one for the sake of the example, and count how many times this happens. So the strategy will be to, for each of the arrows of the Gauss diagram, well, each such arrow will occur, corresponds to a crossing of the knot, so it will occur in one of the crossing fields. So I will first decide which crossing fields correspond to which arrow. So say this arrow comes from the crossing field fk1, and the second one comes from the crossing field fk2, and then I'll sum over k1 and k2 how many contributions come from these particular from crossings which fall within fk1 and fk2. Now, if you suppose I've chosen that this crossing comes from crossing field fk1, then it means that the head, and suppose fk1 was, I don't know what, this one. This means that the head of this arrow must be, meaning the understrand of the corresponding crossing, must be one of the red strands that go through F3, and the tail of, meaning the overstrand of this crossing, must be one of the green strands that go through F3. So for each arrow in the Gauss diagram, I have a bucket or 2 buckets, one bucket at the beginning and one bucket at the end, of where this arrow could have come from. So B1 would be the set of red strands going through F3, and B3 would be the set of green strands going through B3. Now, so really, once I've chosen the crossing fields, I get, well, 2D, in this case, 4, so 2D buckets. And there are two functions defined on these buckets. So one function, T, is the time along the timeline of the knot. So basically the serial number of the strand as I go along the knot. And the other function, Z, is the Z coordinate of the corresponding strand. And then at the end, the combinatorial problems that I need to solve is the following. So given alpha j and beta j, so these indicate the tails and the heads of the strand, of the arrows. And these are numbers from 1 to 2D, where j runs from 1 to d. And given 2D buckets, these are these sets bi, and given a function T, the timeline of the knot on the buckets, and Z, which is the Z coordinate, and it's injective on each individual bucket, I want to compute the size of the set A, where the set A is the set that would correspond to the arrow diagram that I was talking about. So this is the set in which you choose one, so you choose a point B in the Cartesian product of the BIs, namely you choose one element from each bucket, meaning for each crossing field, you choose which one will be the over and which one will be the under strand. And the conditions are that along the knot, they are organized in the correct order. So the time of B1 is less than the time of B2 is less than so on. And also that for each pair of buckets which are connected by an arrow, meaning which correspond to the same crossing, I want the Z coordinate of the alpha side to be the Z coordinate less than the Z coordinate of the beta side. So this is now a combinatorial problem. It has nothing to do, it no longer mentions knot theory. And fortunately, I had my son to ask, Itai, and he very quickly told me that this computation can be carried out in time proportional to L to the D. And therefore, the overall computation can be carried out in time. So I have to choose D crossing fields for the D crossings. Now, there are L squared crossing fields. So the choice of the crossing fields there are L to the 2D choices. And for each choice, I have to apply the Bar-Natan proposition. It's not me, so I can call it Bar-Natan's proposition. It's another Bar-Natan. And the computation takes L to the D. So overall, the computation time is L to the 3D, which is the volume to the D, as claimed. Now, I'm running out of time, so I cannot tell you how to prove this Bar-Natan proposition, but here are 3 slides that do it very quickly. Well, there's something clever going on. It's not at all trivial. So basically, you know, maybe I'll run 20 minutes, or 20 seconds over time. So basically, first of all, you ask yourself, how can you compute a similar thing, but without the limitation on the Z coordinate? And this turns out to be relatively easy. And then, you still have a limitation on the Z coordinate. So the Z on the beta side must be greater than the z on the alpha side. So you only have to count instances that occur within a triangle. And the way you do it efficiently is you decompose the triangle into many squares, in which, inside each of which, so basically inside each of which there is no further condition. Inside each of which you fall into the previous lemma. Fortunately, there aren't too many such squares, and so the computation can be carried out in time as promised. And well, I'm quitting at time as promised. So thank you.